with live classes for all the students, all my colleagues, all the teachers. So here today I'm going to come with the explanation in short. That means I'm going to revise the first chapter of 12th chemistry, that is solid state. Now students, before I revise the topic, before I give you the important tricks to remember for your board exams which are coming soon, these points are really going to help you to crack your board exams with flying colors. But first students, let us understand what is Eduauraa. Yes, Eduauraa is a digital learning platform. It is a digital e-learning platform which is available all over India, students. It is a platform which is available to all the students at affordable rates or affordable prices. Now, students, what are the courses or what are the subjects that Eduauraa brings to you? It brings to you subjects of classes 6 to 12. That means Eduauraa teaches you, gives you guidance from classes 6 to 12. Along with that, students, Eduauraa also teaches you or prepares you for the IIT, JEE and NEET examinations. Yes, students, Eduauraa not only from 6 to 12, IIT, JEE, NEET, and along with that, Eduauraa also brings to you spoken English. And don't forget, students, Eduauraa is preparing you for competitive exam services, that is IAS, NS, and banking services like CA and CS. So students, Eduauraa is a platform where everything is available for you. Now you will ask me, what are the contents of Eduauraa app? Eduauraa contains ebooks, mind maps, subjective questions, that is short answers and long answer questions with proper solutions, well-designed syllabus. You have video lectures with 2D and 3D videos. That is, students, you have interactive video lectures over here. And then along with that, students, you have performance monitoring platform. So students, Eduauraa is a place where you have to come for your educational purposes. All your needs will be satisfied over here. So what are you waiting for? Download the Eduauraa app and go for a 14 days free trial. Yes, students, because this is considered to be India's one of the best selling platform of education. Now, students, for today's lecture, myself, Mohammad Farooque, is going to explain to you in short or revise to you the important concepts or important topics of the chapter solid state. So without wasting much time, students, let us move. Okay, so the chapter is solid state. That I've already told you what you study in solid state. Now, in class 11, when you study states of matter, there you study the differences between solids, liquids, and gases. Yes, but when it comes to 12th standard, you specifically study one state of matter, that is solids. What are solids, or what are the characteristic features of solids? Yes, we know that solids are substances which have a definite shape and occupy a definite volume. Along with that, they also have a definite mass. Because the solids have a definite shape, mass, and volume, students, we can say that the particles of the solids, whether they are molecules, atoms, or ions, there exists some intermolecular forces of attraction. Those intermolecular forces of attraction are very, very strong. Because the intermolecular forces of attraction are very strong, the particles of the solids are very closely packed together. And when they're very closely packed together, we can say that the intermolecular distance or the intermolecular space is minimum in case of solids. Now we see that the constituent particles, like I just told you, atom, molecules, or ions have a fixed position. That means the position of the particles do not leave. The position does not move. They can oscillate only on their mean positions. Yes, students? So that is the property of solids. Besides that, you can say that the density of the solids is maximum. Why? Because the volume occupied by the solids is minimum. So this property of density, when you compare it with liquids and gases, solids have maximum density. Along with that, you can say that solids are incompressible substances. Now, since your board examination, the first term board examination is an objective multiple choice questions. So you should be prepared with these points. You should know the properties of solids because they can ask you a property and give you different choices related to the property. Once you have understood, students, the property or characteristics of solids, let us move into the next concept of the chapter, that is the classification of solids. Now, solids are broadly classified into two types. Which are the two types? That is crystalline solid and amorphous solids. Now, from the examination point of view, students, you should know the important points of differences between crystalline and amorphous solids. Yes, students? Now, this table in front of you is just all the points of differences which you have to remember. Quickly revising the points of differences. We know that crystalline solids, crystalline, that is crystal. Yes, crystalline solids are solids which have a definite geometrical shape. Why do they possess a definite geometrical shape? Because there is regular arrangement of particles. There is regular arrangement of atoms, ions, and molecules, which gives rise to a definite geometrical structure or a definite geometrical shape. With respect to this point, if you see that amorphous solids, what happens? There is an irregular arrangement of particles. The particles, atoms, ions, and molecules possess an irregular arrangement, indefinite arrangement, due to which what happens? They have an irregular shape or irregular geometry. Yes. The second point of difference is that crystalline solids have a definite or sharp melting point. You can identify the solid, whether it's crystalline or amorphous, based on its melting point. If a solid has a sharp melting point, students, that means what? It's a crystalline solid. Whereas, if they do not possess a sharp melting point, that means the melting point is variable, not specific, then it becomes an amorphous solid. The next point of difference is what? Crystalline solids have a definite heat of fusion. That means fusion or melting. The temperature at which a solid melts is fixed, that is heat of fusion. That means whenever a solid melts into its liquid state, heat is absorbed, right? It absorbs heat and melts. Therefore, the heat of fusion is also definite. Whereas in case of amorphous solid, because the melting point is not fixed, it will have indefinite heat of fusion. Then you have another point of differences. Crystalline solids are rigid and incompressible, whereas amorphous solid cannot be compressed to any appreciable extent. So fine, students, as you go down these points of differences, you have to remember these points of differences, because when it comes to subjective examination or objective examination, the points have to be learned by you. Here, before I go into the next concept, students, one point of difference which I would like to bring to your consideration, students, and that point of difference is the anisotropic and the isotropic nature of crystalline and amorphous solids. Now, students, pay attention. We say that crystalline solids are what? Anisotropic, whereas amorphous solids are what? Isotropic in nature, right? Now, when it comes to the multiple choice question, they will ask you, crystalline solids are what? Anisotropic, isotropic, isomorphic, or octahedral. They might give you 4 different choices, confusing choices. What is anisotropic? You see that the physical properties of crystalline solids change with the direction of the crystalline solid. That means if you study the physical property of a crystalline solid along different directions of the crystal structure, they will be found to be different. Whereas in case of amorphous solids, the physical properties of the amorphous solid remains the same in any direction or in all directions. Okay, so this point of difference is a very important point of difference between crystalline and amorphous solid. Right, student? Okay. So once we have differentiated between crystalline and amorphous solids, once we have understood the points of differences, now students, let us move into further classification. What you have to study in your syllabus next is the classification of crystalline solids. We will be studying in detail about the crystalline solids in this chapter. Now, crystalline solids, the table in front of you is a beautiful table which you can remember, are broadly classified into 4 types: molecular, ionic, network, and metallic crystals. You will ask me, or you should recall yourself, students, on what basis, if I ask you, on what basis are crystalline solids classified into 4 different types? Yes, students? Waiting for your answer. Yes, you will tell me, yes, sir. Depending upon what? Depending upon the particles present in the solid, as well as the binding forces or the forces which are holding these particles together in the solid. Yes. So which are the 2 factors that decides the classification of crystalline solids? One is which particles makes up the solid crystal, and number 2, the forces or the bonds which are holding these particles together in the crystal structure. Now we know that molecular crystals, these molecular crystals are further classified into 3 types: non-polar, polar, and hydrogen bonded molecular solids or molecular crystals. Now in case of molecular crystals, remember in short, students, which are the particles of the solids? Molecules. If the particles are molecules, it forms the molecular solids. If the particles are ions, cations and anions, it forms the ionic solids. Network crystals or covalent crystals, if the particles are what? Atoms, then it forms a network crystal. And metallic crystal, it is the atoms of the metals. When it is the atoms of the metal in specific, it forms metallic crystals. Molecular crystals, the binding forces are what, if I ask you? Right. You'll say, sir, the molecular crystals are held together by intermolecular forces of attraction. Go back to your 11th standard. When you study the states of matter, there you study the different intermolecular forces of attraction. Yes, which are the ones? Revise quickly. Yes, dipole-dipole interaction. Yes, ion-dipole interaction. Ion-induced dipole interaction. Yes, or Debye forces or London forces. Correct. Now, in case of molecular crystals, if molecules are the particles, which are the forces that are binding the non-polar molecular crystals? The forces which is binding the non-molecular or non-polar molecular crystals is your what? London or Debye forces. Yes. Then your polar molecules are held together by what? Dipole-dipole interactions. In case of non-polar molecular crystals, example H2, Cl2, O2, etc. Correct? Then when it comes to polar molecules, you have DHF or HCl. Right? Those are the examples of polar, which are held together by what forces? Dipole-dipole interactions. And hydrogen bonded. You know that hydrogen bonded molecules or hydrogen bonding is a very important concept. Hydrogen bond is a bond which exists between hydrogen and a more electronegative element like what? Fluorine, nitrogen, and oxygen. Hydrogen bonded molecular solids, water, ammonia. Yes, students? So these are the examples of hydrogen fluoride. Moving to ionic crystals. What are the particles? Ions, that is cations and ions. Held together by what? Held together by the ionic bonds or Coulombic forces or electrostatic force of attraction. Then you have the network crystals or covalent crystals, in which the molecules or particles are what? They are the atoms. Examples of them will be what? That is silica, SiO2, which forms the network crystal, solid crystal, which you have seen the structure. Graphite, diamond, silicon carbide are all examples of network crystals. And in case of metallic crystals, students, you know that It is the forces which exist between positively charged cations and the mobile free electrons. Whenever a cation loses electrons in the solid crystals, the cation is surrounded with the free electrons. So there is an electrostatic force of attraction between the positive cation and the negatively charged electron. And that gives rise to the metallic bond. So the metallic bond is a bond which is binding the metal atoms in the solid crystal. Now I have explained to you briefly the classification of crystalline solid, which is again summarized for you students in a tabular form. This table you will get in the textbook. This table you will get it while you're watching the video. This table here you can see that the classification, the type of crystalline solid, which are the particles present, the constituent particles that makes up the solid. Then you have the type of bonding that is holding the particles together. And then you have number of examples. Yes, students? So you should be able to decide that based on the example, you should add that example belongs to which type of crystalline solid. Okay, you should be analyzed. Your knowledge of chemistry should tell you, yeah, this particular example belongs to an ionic crystal. This particular example of diamond and graphite belongs to a network crystal or a covalent crystal. Yes, students, is this clear? I hope you're understanding this, students. And these are the points to be kept in mind while you're preparing for your board exams. Once we have understood the classification of solids and the classification of crystalline solids, let us move to the next concept. Let us see what is the next concept in front of you, students. Yes? Now, we are going through the important concepts, so don't forget that, students. Okay? We are trying to understand next is an important concept, that's crystal systems. Now, students, before I explain to you what is a crystal system, you need to understand certain terms involved in this concept. Just let us revise. Solids are a three-dimensional crystal structure. Solids have a three-dimensional crystal structure, right? Now, this three-dimensional crystal structure, when it is represented on paper, when it is represented, it forms a crystal lattice or it forms a space lattice. Those particles of the crystal solid, which are those particles? Atoms, ions, and molecules, which forms the crystal structure. Those particles in a crystal lattice or space lattice are called as lattice points, right? Now, this crystal lattice or space lattice is a representation of the or an arrangement of the three-dimensional geometrical crystal structure of a solid. Lattice points, when you join the lattice point with straight lines, it forms a space lattice or a crystal lattice. Yes? Now, students, this crystal systems is broadly classified into two types. Now, before I go into the classification, you need to understand what is a unit cell. What is a unit cell of a crystal space lattice? What is a unit cell? A unit cell is a repeating unit. It is a part of the crystal structure when repeated again and again forms a complete crystal structure. That means the fundamental part of a crystal structure on repetition forms a complete crystal structure or a crystal lattice. A unit cell has different symmetries. What are the different unit, or you can say that, what are the elements of symmetry of a unit cell? A unit cell has sides, which are represented as what? A, B, C, small letters. Then a unit cell has angles, which are represented as what? Alpha, beta, and gamma. Yes? Then you have the symmetry, that is diagonal symmetry, then you have plane of symmetry. All that concepts you have studied, and if you want to understand those concepts in detail, you have to watch my videos on Eduauraa app, because there I have taught those concepts in detail, students. Okay, so to get the detailed concepts, get the detailed understanding, you have to go down to Eduauraa app, download the app, and watch my videos over there with the animations which are in 2D and 3D. Now, students, coming to the unit cell. I told you unit cell. The unit cell are broadly classified into two types, which is the smallest part of a complete crystal structure is classified as primitive unit cell. And second is centered unit cell. Now, what is a primitive unit cell? Primitive unit cell is a unit cell which consists of only lattice points, or which consists of only molecules or particles at the corner of the unit cell. When the particles are present only at the corners of a unit cell, it becomes a primitive unit cell. And a centered unit cell is a unit cell which consists of corner particles, corner atoms, along with what? A particle in the body or in the face of the particular unit cell. So first let us go into the classification of primitive unit cell. You can see that there are 7 types of primitive unit cells. Now this table is of great importance to you students. Yes, these primitive unit cells, there are 7 types of primitive unit cells or 7 types of crystal systems. Here you can see the crystal systems are of 7 different types: cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, and rhombohedral. These 7 crystal systems, they have only lattice points at the corners of the unit cell. But these 7 crystal systems are divided into 14 brevis lattices or 14 brevis units. If you see that under the brevis lattices, cubic has 3 types of brevis lattices, that is primitive, face-centered, and body-centered. So now students, you can identify the particular crystal system based upon what? Based upon its intercept, that is the sides. A is equal to B is equal to C. When all the sides are equal, we say that belongs to the cubic crystal system. Along with that, you can say that the 3 angles, alpha is equal to beta is equal to gamma is equal to 90 degrees. And you have to remember examples based on that type of crystal system. So here we see that students, the 7 crystal systems are divided into 14 brevis lattices. Okay, and you have to remember this table that for the particular crystal system, it can be identified by what? The sides, whether they're equal or not equal, and their angles, whether they're equal or not equal to 90 degrees or less than or greater than 90 degrees. So this table is there with you. You can go through this table and understand what you have to remember for the primitive unit cell, which are divided into 7 crystal systems and 14 brevis lattices. The second type of unit cell is what? Centered unit cell. Now in the chapter, you will be concentrating on these 3 types of unit cells. Yes, there are 3 types of centered unit cell, which are body-centered, face-centered, and end-centered. What is a body-centered unit cell? Along with the corner lattice points, it contains one constituent particle, one lattice point at the body or inside the body of the unit cell. I'll be showing you the diagrams next further. Okay, face-centered unit cell contains what? It contains the corner atoms, the particles at the corner of the unit cell. Along with that, it has atoms in the center of each phase. Okay, if it's a cubic phase, if it's a cubic unit cell, there are 6 phases. So there will be 6 phase atoms and there will be 8 corner atoms. End-centered is what? It contains 2 phase atoms. Any 2 phase, center of 2 phases, there will be atoms along with the corner particles. So this is what you're supposed to remember for the centered unit cell classification. Now students, once we have understood the classification of unit cell into primitive and centered and different types and their explanation, as far as your syllabus is concerned, there are 7 crystal systems, but out of that you study only 1 crystal system in detail for your boards, and which is that the cubic crystal system, which is the first one, in which all the sides A is equal to B is equal to C, and all the angles alpha is equal to beta is equal to gamma is equal to 90 degrees. In that crystal system, there are how many Brevis lattices? 3. Which were the 3? Yes, I just explained you the 3. Simple cubic, body-centered, and face-centered cubic crystal cell or unit cell. Now, students, for these 3 Brevis lattices or 3 unit cells under the crystal system cubic or the cubic crystal system, you have to calculate, or you know that you should know from the objective point of view, that is the number of atoms present in each unit cell, number of atoms, total number of atoms present in the unit. Now you know that in a simple cubic crystal that I chose to you, this is a simple cubic unit cell in which you can see there are 8 corner atoms or 8 lattice points. How do you calculate the number of atoms? The number of atoms in the corner are 8. Contribution from each corner atom is how much? Contribution from each corner atom is 1 by 8 to a unit cell. Yes? The contribution is 1 by 8. Corner atoms are shared by how many unit cells in total? 8. So, contribution per atom is 1 by 8. Yes, per unit cell is 1 by 8. It's shared by how many unit cells? 8. So 8 into 1 by 8 will be equal to 1. Yes, because there are only corner atoms, the number of atoms in the face is 0. The number of atoms in the body center is 0. So total number of atoms belonging to that 1 unit cell, that is a simple cubic unit cell, is 1. I'm just going into detailed explanation, but you have to remember, simple cubic unit cell number of atoms present in the unit cell is 1. Similarly, number of atoms present in body centered cubic unit cell is how much? It is 2. And face centered is how much? 4. But in brief, in body centered, you have 8 corner atoms and 1 particle, 1 lattice point inside the body. The contribution from the corner atom is how much? For 1 unit cell, 1 by 8. Each corner atom is shared by how many other unit cells? 8. So 8 into 1 by 8 will be 1. The atom which is present, or the particle which is present, or the lattice point which is present inside the body belongs only to that unit cell. It is not shared with any other unit cells. That only belongs to that unit cell. So 1 plus 1 makes it 2. And when it comes to the face-centered cubic unit cell, I told you in the beginning, or some time back, that a face-centered cubic unit cell has 8 corner atoms and 6 phase atoms. Now, the contribution of each corner atom is 1 by 8 into 8, because shared by 8 unit cells. The contribution of each phase atom is 1 by 2. Each phase atom contribution is 1 by 2. How many phase atoms are there? 6. So 6 into 1 by 2 is equal to 3. So contribution from the corner atom is 1. Contribution from the phase atom is 3. So total number of atoms present in an FCC, short form is what? FCC type of a cubic unit cell is 4. So SCC is simple cubic, BCC is body centered, and FCC is face centered. Number of atoms present in the unit cell is 1, 2, and 4 respectively. Dear students, so these are the points to be remembered, because that will also help you for calculation of density. That will also help you for the calculation of packing efficiency. Now let us understand, students, what is packing efficiency? We know that in case of solids, there is a regular arrangement of particles. The interparticular space or intermolecular space is minimum. Yes, because the intermolecular space is minimum, the particles are very closely packed or arranged. But you see that the packing efficiency in the cubic crystal solids is not 100%. Yes, the packing efficiency, how it is calculated, if I ask you? Yes, you tell me that the packing efficiency is equal to volume occupied by all the atoms present in the unit cell. All the atoms present in a simple cubic unit cell is 1, 2 in BCC, and 4 in face centered or FCC type. Volume occupied by all the atoms present in the unit cell divided by the total volume of the unit cell. Because it's a cubic crystal structure, we know that the volume of the cube is side cube, that is A cube, multiplied by 100. When you multiply by 100, you're going to get the packing efficiency in terms of percentage. Now, this table in front of you, very important table for calculations. These formulas have to be learned by you for the 3 unit cells or brevis lattices for the cubic crystal system. Simple cubic, that is relation between R, radius, and side or edge length A. R is equal to A by 2. Volume of that particular atom is given by 4 by 3, A cube by 2. Then you have the packing density, which is given by pi by 6. Pi by 6 will be 3.14 divided by 6, which comes as 0.52. That is the packing efficiency in terms of fraction is 0.52. In terms of percentage, is how much? 52%. Packing efficiency is 52%. That means void or empty space will be how much? 100 minus 52, that is 48%. So you have to remember, in case of simple cubic, the formula of radius, then the formula of volume, and the packing efficiency or density in terms of decimals and in terms of percentage. Coming to face-centered FCC, radius is given by formula A by 2 root 2. Yes. Then you have the packing efficiency is 0.74, that is 74%. Highest packing efficiency in case of FCC type. Vacant or void space will be 26%. And in case of BCC, you have the packing efficiency is 0.68, that is 68%. And empty space is 32%. So students, these are the packing efficiencies. You must remember the values along with the formula of radius and volume of the particular unit cell. So revise these formulas, make a note of these formulas and keep them in mind, because calculations are only based on formulas. Simple substitution. They'll give you R and ask you to find out A. R is radius, A is edge length or side length of the cube. Any one value will be given, the other has to be determined. Simple substitution and calculations. That's it, students. That's why chemistry numericals are very, very simple. Unless you know the formulas and its application, you cannot get full marks. Now, once you have understood this concept, students, then another formula on which you have numericals or problems to be solved is the density of a crystal lattice. How do you calculate density? We know that density is the ratio of mass per unit volume, right? Mass per unit volume of the unit cell. That is mass of the unit cell, total mass of the unit cell divided by the volume of the unit cell. Now you will ask me, sir, mass of the unit cell. How do you calculate mass of the unit cell? Mass of the unit cell is determined by the molar mass or atomic mass of that particular element or solid or a metal multiplied by Z. Now Z is here what? Number of atoms present in that particular unit cell. How do you know Z value? Z I just told you, if it is simple cubic SCC, Z is equal to 1. Number of atoms is 1. BCC it is 2 and FCC it is 4. Yes. So Z multiplied by molar mass, which will be given to you. Molar mass will nothing be atomic mass of the element or a metal. Molar mass of the compound will be given to you. Divided by volume. Volume of the unit cell is A cube. Edge length will be given to you. Edge length of it is given to you in centimeter. Then your density will come in centimeter cube. Yes. Then multiplied by Avogadro's number, Ne. Why do you multiply? Because you have to convert that particular molar mass, because you have the number of particles. Number of particles is 2. So you're converting the number of particles in terms of mass. You divide by Avogadro's number. So what is the formula to be remembered, students? The formula to be remembered is this. This formula has to be remembered for calculating density. Z is number of atoms present per unit cell, depending upon whether the unit cell belongs to simple cubic, body centered or face centered. Molar mass divided by volume A cube into N. So now they can ask you to find out any one of these variables depending upon the numerical. So one formula, substitution and calculations. Okay. Once we have gone through this, let us quickly go through the arrangement of particles. Yes, arrangement of particles in solids. You have in crystal solids, you have one-dimensional arrangement. That's a linear arrangement where you see that each particle of the solid, whether it's molecule, atom, or ion, is represented by a sphere. This is the linear arrangement, horizontal linear arrangement, where you can see each particle touching each other. Okay, so this is called as one-dimensional arrangement or one way of arrangement. Yes. Then you have is two-dimensional arrangement. The two-dimensional arrangement are of two types. One is square close packing, and other is what? Hexagonal close packing. What is the difference between the two? You know this, students. Yes. In case of square close packing, you have a type of arrangement. That means what? You have a one-dimensional linear arrangement of spheres. Then you have a next set of spheres on top of each other. So here, if you see that very clearly, that you have 1, 2, 3, 4, all one top of the other. The spheres are one top of the other. Why it is called as square close packing? Because if you consider any one, you see that there are 4 surrounding neighbors which are equidistant. Yes, and when you join those centers, when you join the centers of these 4, it forms a square close packing. Correct? So this is linear, one top of the other, makes it a type of arrangement. Then you have is the hexagonal close packing. What happens in case of hexagonal close packing? You have a regular linear A, then you have a B layer, but the particles of B, the spheres of B, are not top of the particles of A layer. They're in between. You can see that. They're in between. So you have AB type of arrangement. And then AB type of arrangement, whenever you consider one particle at the center, it is giving you how many? 6 hexagons. So it forms a 6 hexagonal close packing system. Now, because of this arrangement, you can see that there is some space or gap, empty space. That empty space or gap is called as voids. Therefore, a cubic crystal structure does not have 100% packing efficiency. We have seen that there is a void space as well as those are called as empty spaces. Now, once moving to the three-dimensional arrangement of particles. In the three-dimensional arrangement of particles, because a crystal structure is a three-dimensional crystal structure. Now, in the three-dimensional crystal structure, if you see that, you have, if you consider an A type of layer, you have A type of layer, okay, A type of arrangement, a two-dimensional A type of layer, one top of the other. Or you can have an AB type of two-dimensional arrangement, one top of the other. Which will again give rise to what? It will give rise to what? Square close packing or hexagonal close packing, three-dimensional. Okay, so this you have studied. This is just a revision to you for the different types of packing in crystal structure. Now I told you that, I showed you that whenever there is arrangement of particles in two-dimensional or three-dimensional arrangement, gives rise to voids. There are two types of voids which you have to remember. That is the octahedral and tetrahedral voids. Now this point which you can see, this slide in front of you is very important for calculation. Keep in mind, you can solve the question in 1 second. Number of octahedral voids is equal to what? Number of octahedral voids is equal to number of effective atoms present in the unit cell. That means the number of atoms in the unit cell is 1, number of octahedral voids is 1. If it is 2, it is 2. If it is 4, it is 4 in case of FCC. But number of tetrahedral voids is 2 times the number of effective atoms present in the unit cell. That means if I ask you students, what is the relation between octahedral voids and tetrahedral voids? Yes, you will tell me that number of octahedral voids, no, number of tetrahedral voids is equal to 2 times the number of octahedral voids. They ask you in a question, a particular crystal solid has 2 tetrahedral voids. Find out the number of octahedral voids. So this relation will help you. Number of tetrahedral voids is equal to 2 times the number of octahedral voids. This diagram, this slide shows you very nicely the three-dimensional arrangement, which is only one side. You can see in one side horizontal, where they show T and O, the space of the gap. Where they're showing the tetrahedral and the octahedral voids very nicely. The space or empty space, which is leading to the tetrahedral and octahedral voids. Yes, students. Now, when it comes to ionic crystals or ionic solids, students, in specific, you can identify the shape of the ionic crystal. You can know its coordination number based on the radius ratio. What is coordination number? Coordination number is the equidistant neighboring atoms or equidistant neighboring particles present in a unit cell. Now, this table you have to remember. If they tell you that the limiting radius ratio, what is radius ratio? Ratio of cation to ratio of anion. That is radius of cation divided by radius of anion will give you the radius ratio. If it is less than 0.155, the solid, ionic solid has a coordination number 2 and the shape of that solid is linear. So this table will tell you based on the radius ratio value, you can determine what? The shape of the ionic crystal as well as you can identify its coordination number. Fine, students. So this table again has to be learned by you and remembered by you. Now this table is only for your reference, students, that there are types or ionic structures, different structures are given to you. There are descriptions of the structure and the examples. This table is there in the NCERT textbook. Go through the table and just remember, because there you have to remember the coordination number for the particular type of crystal structure in case of ion. Coming to the last important concept of the chapter, students, that is defects in solids. Defects in solids or imperfections in solids. What are defects or imperfections in solids? The solid defects or imperfections in solids arises due to what? Arises due to the absence of particles or missing of particles or misplacement of the particles. That is, defects in solids are classified as impurity defects, stoichiometric defects, and non-stoichiometric defects. Yes, you have defects which are called as point defects and line defects. Point defect is only one individual particle is missing from the whole crystal structure. One cation or one anion is missing, becomes a point defect. If a row of cations or anions or particles are missing, then it forms a line defect. But under the stoichiometric defects, you see that you have Schottky defects, Frenkel defects, vacancy defects, and interstitial defects. Under non-stoichiometric defects, you have is the metal excess defect and metal deficiency defect. This concept is summarized for you, students, in proper diagrammatic way. You can see these figures. Vacancy defect. Here you can see that there is cations and anions A and B respectively. Yes, but if there is missing ion, if there is an ion missing from the complete crystal structure, there is one ion missing, that leads to vacancy defect. Yes, and because of this, what happens? The density of that particular solid decreases. Then you have a Frenkel defect. In Frenkel defect, what has happened is, if you see that one positive ion, one cation, has left its original position, has left its mean position, and moved inside the solid crystal, in somewhere inside the solid crystal. It has left its position and moved somewhere away, but it is not left the solid crystal. It is there inside the crystal, but it is moved to a new position, and that gives rise to Frenkel defect. Then here you see what is an interstitial impurity defect. Whenever a vacancy defect is caused, whenever one particle is missing from the solid crystal and it is occupied by an impurity, it is occupied by any other ion, then it forms an interstitial impurity defect. Yes, students? Then here you see that what are F centers. Now F centers are again defects which are occurring whenever, if you see that a cation has left its original position, cation has left its position, but that position is occupied by an electron. Whenever an electron occupies the position of a cation in the crystal structure, gives rise to F center, which results in the color formation of that particular solid, which is generally seen in case of transition metals. So students, we have revised the chapter nicely for you. We have revised in short for you. But my humble request to you students, you want a detailed explanation for this chapter, you will have to download the Eduauraa app. Yes, students. So what are you waiting for? Immediately download the Eduauraa app. Go for the 14 days free trial. And don't forget that, students. Once you like the Eduauraa app, then go to the YouTube channels of Eduauraa live classes, subscribe the channels, like the channels, and share it with your friends. Because Eduauraa is the only platform which gives you complete education in all the different courses at very reasonable prices. So for today, your chemistry expert, Mohammad Farooque, is signing off. Have a nice day, students, and enjoy learning with Eduauraa. Thank you.